driving the galaxies further and further apart to a dismal fate. Combined, dark matter and dark energy make up 96% of the universe. And uncovering their secrets is like making the 1 in a million shot. If uncovered, the ultimate fate of the universe might be revealed. Will it crash and burn in a horrific collision of gravitational forces? Or will dark energy tear the universe apart?
The betting is the universe will die in ice.
Understanding these two quantities, dark matter and dark energy, is really fundamental to understanding the universe.
This is a trip to the dark side of the universe. This is the hunt for dark matter and dark energy. Dark matter is unlike anything we have ever encountered on Earth. Billions of these strange particles pass through everything they encounter each second. They are so massive in weight, they have the power to influence the galaxies, how they form, and how fast they spin. Dark matter's invisible presence is everywhere, or so it seems. Science has not directly proven dark matter particles exist. There are many suspects, but no answers. And observing something you can't see isn't easy.
It doesn't emit light and it doesn't absorb light. It doesn't interact with light at all.
Not only does it not shine, you can't easily see it in obscuration.
But the evidence is there. Science knows it.
Every textbook on the planet Earth says that the universe is made out of atoms and some subatomic particles. Well, all those textbooks are wrong.
And they are going underground to prove it.
When they hear about this invisible matter called dark matter, they say, bah, humbug, show me proof that dark matter exists.
Sudan, Minnesota, 200 miles from any major city lights. A perfect place for hunting dark matter, but not for obvious reasons.
So you'd think we'd want to look up in the sky for dark matter. That's where dark matter's coming from, after all. But instead, we're going to don our helmets and we're going to walk down into this mine.
2,431 feet underground is the Sudan National Laboratory, an abandoned iron mine reconfigured into a research facility. This is just one lab of many around the world going underground to shield experiments from cosmic rays. Each are racing to detect dark matter, an invisible particle that has only been indirectly observed, but never captured.
We've been at this for now a decade, and we have yet to see a dark matter particle.
The hunt for dark matter started almost a century ago. Astronomers finally had the tools to see deep into the night sky, and the questions began.
So it wasn't until the 1920s that the technology developed well enough so that we could take little fuzzy patches that people had noticed in their telescopes and resolve them and figure out what they are.
Then Edwin Hubble shocked the world and declared the universe was bigger than just the Milky Way.
People realized that some of these little fuzzy patches are separate galaxies, just like our Milky Way galaxy.
As astronomers discovered new galaxies, Caltech professor Fritz Zwicky looked up to the neighboring Coma cluster of galaxies and observed something strange.
When he measured what the motions were in the Coma cluster of galaxies, he got an estimate for how much mass there was in that cluster. Then he compared it to how much mass you could actually see by looking at the galaxies.
Something didn't add up. The galaxies were moving too fast within the cluster for the amount of illuminated stuff he could see. By his calculations, there should have been 160 times more illuminated mass to account for the random speeds of galaxies in the cluster. Something else was affecting their motions. But what was it?
he analyzed their motions and concluded that the cluster could not be stable unless there was a large amount of dark matter present. In 1933, he was one of the first people to really grasp the significance of the presence of dark matter. He called it missing matter.
Dark matter, an invisible mass that was gravitationally attractive and was able to affect the speeds of entire galaxies in a cluster. Revolutionary thinking, yes, but the discovery was largely ignored.
I think that people took Zwicky seriously, but they didn't jump to any conclusions. This was a time when the universe was just beginning to be explored. It was the 1920s when we first realized there were galaxies outside our own. What we didn't know back then was whether it was simply galaxies or stars or gas or dust that we couldn't see, or whether it was something truly different.
Zwicky's observations were based on measuring the mass in the stars and galaxies. But how do you weigh stuff in space?
You can't go and put the sun on a scale. That's a little bit hard. But what you can do is you can measure how fast the planets are moving around the sun. And the more stuff there is in the sun, the faster those planets have to move to stay in their orbits.
Newton and Einstein both said the more mass or stuff you have in an object, the more gravitational pull it will have. And the further an object is from the center, the slower it should travel in orbit, because the gravitational pull is weaker.
According to Einstein's general theory of relativity, or even according to Newtonian gravity, all of the galaxies are pulling on each other.
It's like the sun's influence on our solar system. The mass of the sun pulls Mercury faster than Pluto because Mercury is positioned closer to the sun.
Likewise, for a galaxy, you would expect that as you got further and further away, things are moving more and more slowly to stay in their orbits.
But Zwicky didn't observe that. Neither did a young scientist named Vera Rubin 50 years later. She was observing the rotational curves of galaxies similar to the Milky Way. Like Zwicky, her observations also seemed strange.
What Vera Rubin actually measured was that you got further and further away, the velocity of the orbiting gas and dust remained constant.
What Rubin observed was as if a city were a galaxy and every car on the road was a planet or star. And despite the amount of traffic, every car traveled around the city at the same speed. This same consistent rotational speed, despite the amount of stuff or traffic, was exactly what Rubin observed.
The outer parts of the galaxy were rotating fast enough that there must be a lot more mass, otherwise the galaxy would have flown apart.
The only way to resolve this paradox of galaxies which spin 10 times too fast is to assume that there is a halo of invisible matter surrounding the galaxy, keeping the galaxy whole.
Dark matter was present in the galaxies, and it had enough mass to keep the rotation speed constant.
Imagine that I am the dark matter. This ball is a star orbiting me because my gravitational force is keeping it in place. But even if you couldn't see me, you would know that there must be something here, otherwise the star would just zoom off in a straight line. There must be something causing that gravity, and that's how we know that there must be dark matter.
Rubin estimated that there was 10 times more dark matter than ordinary illuminated stuff.
Since then, we've analyzed hundreds of galaxies, and they all have the same pattern. They all rotate too fast for their own good, and they need dark matter to hold them together.
This time, science paid attention and started to wonder, what is dark matter? How do you find something that is invisible in space? They needed to see just where dark matter was hiding out in the universe. And even if they couldn't see it, science realized that dark matter exposed itself by bending light that passes through it. It's called gravitational lensing, and it's a virtual spotlight that uncovers any invisible stuff in the universe.
What it does do is it does what all matter does, and that it can deflect the light ray. So a light ray can be deflected in its path by dark matter.
By tracing the battered light's path, gravitational lensing detected dark matter concentrated in the halos of galaxies. gravitational lensing proved to be infallible, and dark matter's presence was suddenly revealed.
This technique of gravitational lensing is the most precise because we can actually pinpoint not just how much dark matter there is, but how it's distributed in its position on the sky. And that's because we can measure the distortion of the light rays passing through the dark matter.
How do you know that your glasses are there? Because it bends light. In the same way, by looking at Hubble space pictures of the universe and looking at the distortion of light as it goes through galaxies, we actually have maps of dark matter.
Most of the mass of a galaxy is from the dark matter. The ordinary matter accumulates in the gravitational field of the dark matter.
But once dark matter came on the scene, scientists wondered if it was a new, undetected particle or just invisible, ordinary matter.
When people found dark matter, everybody wanted to know, well, what is it, you know? And of course, the first answer is it's just the stuff that makes up you and me, but it's not shining.
Scientists started to investigate objects in the universe that didn't emit light. Black holes were considered. They don't emit light, can draw matter to themselves, and are detected with gravitational lensing.
It could take the form of black holes or machos, massive compact halo objects, which are basically dark, small stars that don't give off a lot of light.
Machos hide out in the halo of the Milky Way and are detected by gravitational lensing. But there weren't enough to account for the amount of dark matter needed. Failed stars like brown dwarfs were also suspected. They are massive enough to make up dark matter's presence. Whatever dark matter is, there is way more of it than the ordinary matter of stars and planets. 10 times more.
All of the stuff that you can construct from ordinary atoms, protons and neutrons and electrons, cannot possibly be enough to account for the total amount of matter that you see in galaxies and clusters.
Scientists continued to present new suspects as the search continued for dark matter. Previously discovered exotic particles like neutrinos were reconsidered. Like dark matter, neutrinos are passing through the Earth millions of particles at a time. But they are too light to account for dark matter's effect on gravity. And scientists can recreate neutrinos in particle colliders. They also come from the sun.
Axions is also another possible dark matter candidate. They were invented to explain a particular glitch in one of the particle physics theories. They would be extremely light, so you search for them in a completely different way than what we're doing. But they would also be very numerous, and so they could possibly be the dark matter.
Axions are very light and are believed to have been created at the moment of the Big Bang, just like dark matter. But theories suggest that they can change to protons, while dark matter is stable. After exhausting all the usual suspects, many scientists believe dark matter is a new exotic particle, unlike anything on Earth. And billions are passing through us every second. Up until the discovery of dark matter, scientists believed the universe was made only of protons, neutrons, and electrons, the stuff everything on Earth is made of.
And we know it has some mass, and we're left with something that we've not yet detected.
But to be a perfect dark matter candidate, it must have certain physical properties, and none of the usual suspects were fitting the crime.
So we know that the dark matter is some ponderous substance. We know that it's not moving too quickly, and we know that we can't see it.
Dark matter particles are not traveling at the speed of light, and they don't interact with you and me or anything pretty well, and that's why it's been so difficult to track down these particles.
And it doesn't interact with ordinary matter except through gravity. If I had some dark matter in my hand, it would have weight, but first it would dissolve right through my fingers.
There aren't any candidates for cold dark matter within what we call the standard model of particle physics.
Like an invisible man passing through walls, dark matter is passing through Earth billions of particles at a time, never colliding with ordinary matter.
So the most popular idea for what the dark matter could be is something called a WIMP.
WIMPs are weakly interacting massive particles. They have not been detected, but their characteristics match the perfect dark matter candidate. At the Sudan laboratory, the Fermilab team has gone underground, braving thousands of bats to try and capture a WIMP particle.
This is called the Cryogenic Dark Matter Search. CDMS is the acronym for it. This was an iron ore mine until 1962 when it shut down. We're half-mile underground.
Fermilab has designed a machine that at sub-zero temperatures can detect a dark matter particle passing through it. And its sensor is made of germanium, a dense metal jam-packed with atoms.
It's a very pure block of germanium. It's got on the surface of it a pattern of tiny little thermometers, basically, that are able to detect when a particle passes through this hockey puck-sized chunk of germanium. Dark matter is streaming right through us right now without doing anything. Very occasionally, it will bump into the nucleus of an atom, and that's the signature that we're hoping to see.
To get a clean dark matter hit, Fermilab needed to filter out junk from space.
We would get so many particles that it would be really trying to sift a needle in a haystack.
Fermilab's experiment picks up all matter that passes through this detector. The less junk in the air, the easier it will be to detect a dark matter particle. Because dark matter doesn't interact easily with regular protons and electrons, Fermilab has frozen the germanium pucks to near sub-zero temperatures.
If a dark matter particle comes through and hits a nucleus, it will actually change the temperature of the crystal very slightly. And so we're looking for that tiny change of temperature in the crystal to signal that a dark matter particle has passed by.
16 germanium pucks sit in a chamber inside a clean room.
So we're suited up. We're about to go into the experimental room. It's a class 10,000 clean room. That's why we're all suited up, so we don't carry in any dust, because that would cause a background for the experiment. So let's go inside. So we have scintillation counters that are catching any cosmic ray particles that get all the way down underground here. So right here is what keeps our experiment cold, that tiny little bit above absolute zero. This is a dilution refrigerator. So way inside here are the germanium and silicon detectors. So we're just waiting for a WIMP, a dark matter particle, to get down to this depth and hit one of those germanium and silicon crystals that's buried way inside all this shield.
Fermilab has been visiting the mine for nearly 2 years, trying to capture dark matter. This is far harder than it sounds. Although billions of particles are passing through Earth at one time, it's a 1 in a million shot dark matter will interact with ordinary matter. Getting a dark matter particle to hit a germanium atom is like an archer trying to hit a bullseye when the target is a mile away.
All these green lights indicate particles passing through the germanium and silicon detectors that we saw downstairs. These are almost certainly all background particles, but maybe it's buried in there someplace as a WIMP. But we won't know until we analyze the data.
Hunting dark matter is tedious. Each day, the Fermilab team reports to the underground lab, analyzes data, and perfects their ping-pong game while waiting for the one hit that will prove dark matter exists. But for all this effort and waiting around, no dark matter has been detected by Fermilab or by anyone else.
Unfortunately, we've seen precisely 0 dark matter particles so far.
Any day now, we may have the announcement that physicists have captured dark matter in a bottle.
We have a hypothesis. It certainly seems to explain the universe we live in, but the plain fact is we haven't yet detected this cold dark matter particle.
Finding dark matter will not only give us proof of its existence, but might also answer the other big questions of space.
Detecting dark matter directly will give us a window onto what was going on 1/10,000th of a second after the Big Bang.
If scientists can discover what dark matter is, they might also discover how the universe behaved early in its life.
Dark matter is not only a mysterious quantity in the universe, but also it's fundamental to why we're here, in fact. It would be difficult to form galaxies and hence, the solar system and hence life on Earth.
The story of dark matter and dark energy can't be told without going back to the beginning of time, to the moment of the Big Bang, when space didn't exist.
There is no center where you can point to, and that's exactly the analogy for the Big Bang. There is no direction in the sky from which all the galaxies are expanding.
From this moment of nothing to a violent explosion, space was created, and the universe began to grow from a seed. Particles formed in a nuclear fusion of gas and energy.
Ordinary matter was reacting with other ordinary matter. The early universe was, in fact, a nuclear reactor when it was 1 minute old.
And 300 years later, bits of particles began to cluster, creating the seeds from which stars and galaxies would later form.
Bigger lumps grow to form yet bigger lumps, and so gravity is slowly pulling force, bringing objects together.
What scientists now realize was that at the moment of the Big Bang, dark matter was created. And it played a critical role in helping ordinary matter clump together to form stars and planets. Like steel girders used on a building site, dark matter's slow-moving particles acted like scaffolding upon which ordinary matter could attach itself.
We believe that because it's cold and doesn't interact very much, that dark matter was pulled together by gravity very slowly over time and actually formed the seeds around which normal matter coalesced into galaxies.
It's like a cosmic web, like a spider's web, where there are strands of dark matter, and where these strands intersect, like a scaffolding pattern. So in a sense, the dark matter is the framework. It's providing the scaffolding for the shining galaxies that we can easily see.
Are really like the Christmas tree lights. They're not the actual Christmas tree. They're the things that are visible from very, very far away. But the reality of a galaxy is a big halo, most of which you don't see. You see the shiny bits that are stars and planets that have accumulated at the center of that large halo, which is mostly dark matter.
Scientists have long wondered why galaxies formed in seemingly random patterns across space. Now scientists know it's because of dark matter's gravitational pull.
The universe is not uniform at all, but has voids, it has clumps, it seems to have bubble-like regions. What we now believe is due to dark matter.
In the last year, astronomers have been able to take their theory one step further and create a detailed 3D map of dark matter in the universe using gravitational lensing.
And Einstein said that gravity affects everything, just like gravity is caused by everything. So one of the things that is affected by gravity is light itself.
Because when light goes through dark matter, it bends, just the way light bends when it goes through glass.
And light doesn't discriminate between ordinary matter and dark. Both types of matter batter light's path as it travels through galaxies. Like plotting a course on a map, astronomers have traced thousands of light sources as they pass through dark matter. It has given science the most accurate picture yet of where dark matter hides in space.
We can compare that map of the dark matter with where the galaxies are. And lo and behold, we find that the dark matter is acting as the skeleton. It is the backbone around which the visible material is clumping.
By mapping the universe, astronomers can also look back in time and predict how much matter was created at the Big Bang.
So if you know how lumpy the universe appears now, and when it was half its current size, and when it was half its current size before that, you can infer the total amount of stuff in the universe. It gives us another very nice way of matching on to what we believe is the total amount of dark matter.
It's estimated dark matter makes up 23% of the universe, while ordinary matter makes up only 4%.
You need a lot of dark matter to account for the total amount of gravity that exists in these clusters and galaxies.
But what makes up the final 73% of the universe? Scientists were shocked to discover a new mysterious dark energy was dominating space. And its repulsive energy is driving the galaxies apart. Science always assumed that although the universe continues to grow in size, it would eventually slow in its expansion, or perhaps even collapse on itself. Gravity would overcome any momentum it had. But while measuring the expansion history of the universe, scientists were shocked to realize that the universe wasn't slowing down, it was speeding up. And a grim fate awaited any living thing.
The universe will disintegrate, and temperatures will become so cold that any intelligent life will freeze to death.
From the moment the Big Bang created the universe, space has been expanding and never stopping, carrying galaxies along for the ride.
The space in between the galaxies is expanding, but galaxies are not expanding. The Earth is not expanding, the solar system is not expanding.
Edwin Hubble first discovered galaxies were moving away from the Milky Way in 1929 by realizing the more distant galaxies move faster away from us than the nearby ones. He realized he could measure their velocities by studying their wavelengths through a prism. It's called measuring the redshift and is still used to measure distances in space.
And he found that, in fact, the greater the distance of a galaxy right now, the greater the speed with which it's moving away from us. That is, the greater its redshift.
A few years ago, astronomers decided to use redshift measurements to measure the expansion history of the universe. But how do you measure the entire expansion history of the universe? How do you travel back 12 billion years in time?
We have the capability of going back in time directly to observe the past. So much in the same way as a geologist, looks at layers in the Grand Canyon, and as he goes down into lower and lower layers, looking back in history.
If you look at progressively more distant galaxies, you're looking at them as they were at progressively greater times in the past.
To measure expansion history, scientists used Type 1a supernovas as their standard candle.
One example of a standard candle might be a 100-watt light bulb. You could have a bunch of these things sitting around in your room at different distances from you. Then the more distant ones will appear fainter, and the more nearby ones will appear brighter.
Type 1a supernovas are always consistently brilliant, no matter where they occur in space.
A supernova is the colossal explosion of a star at the end of its life. It just goes kabam! And it occurs when a dying star known as a white dwarf goes through a nuclear runaway and just literally blows itself to smithereens. We find the Type 1a supernovae in very distant galaxies, so they look really faint, and then we compare them with Type 1a supernovae in nearby galaxies whose distances were measured using Cepheid variables or some other technique.
Using these Type 1a supernovas, two different teams set out in the 1990s to measure the deceleration rate of the universe. But to capture supernovas as they occur, Astronomers had to put the universe on surveillance.
You can compare this a little bit to perhaps surveying a casino. So all these cameras are on all the time, and most of the time they don't find much of anything interesting, but occasionally they find what they're looking for. You have to look at lots of galaxies. So what we did is we took large telescopes with cameras that have wide fields of view, about as wide as, say, the width of the full moon. And we took many snapshots of space using this wide field camera. And each snapshot contains tens of thousands of galaxies. And by comparing the apparent brightness of the distant Type 1As with those of the nearby Type 1As in nearby galaxies, we can get the distance of the distant galaxies and hence the amount of time that we're looking back in the history of the universe.
After the two teams studied the results of 60 Type 1A supernovas, scientists were shocked at their results. The universe wasn't slowing down, its expansion was speeding up.
We all expected that expansion to be slowing down with time, because after all of the galaxies are pulling on one another.
We were so confident we were going to measure the rate at which the universe was slowing down, and then we found, of course, a negative answer. The universe is not slowing down, it's speeding up, and this was just a big mystery.
That is really, really weird. You know, we expected to measure some amount of slowdown, and instead it's expanding more quickly. That's like the wrong sign, right? We were really afraid that we had gotten completely the wrong answer. We rechecked our measurements, we checked the analysis. A bunch of people on each of the two teams did the measurements and the analysis independently and kept getting the same result.
One of the greatest shocks in the world of cosmology just in the last few years has been the realization that our universe is accelerating.
This repulsive force driving the universe was called dark energy, an invisible energy that was nothing anyone expected or understood.
It suggests that over the largest distances in the universe, there's a repulsive effect that dominates over gravity.
And dark energy was creating space, taking galaxies along for the ride.
This energy that appears to fill the universe and stretch the expansion of the universe faster and faster with time is now known as dark energy. So here I throw the apple, and initially it's decelerating, and then dark energy makes it accelerate away from me. So you throw the apple, and it just zooms away faster and faster with time.
Like the apple forever traveling into space, galaxies are being carried away as more space is created.
So if you could imagine, you know, a classroom populated by chairs, and those chairs are slowly getting further apart from one another within a classroom. Because if all the chairs are being stretched apart, like in the expanding universe, no matter which chair you sit on, you'll find all chairs are moving away from you. So the chairs are not really expanding. In fact, the chairs are the same size, really. What's happening is that the room is getting bigger. The space in between the chairs is being stretched apart.
More space is being created in between the galaxies. So you have individual galaxies remaining of constant size in a universe where all of space is getting bigger and bigger.
Dark energy is very different from dark matter.
It doesn't clump up like galaxies do in clusters or like stars do in galaxies. Instead, it appears to be pretty uniform, and we find the same amount of acceleration no matter which direction we look at.
It's probably smooth, although some people believe there may be structure in its distribution and its influence.
Dark energy is the energy of the vacuum, the energy of nothing. Even nothingness has energy, and it's pushing the galaxies apart, creating a runaway universe.
It appears dark energy and dark matter have been at war with one another since the beginning of time. Science believes dark energy was created along with dark matter at the moment of the Big Bang. It has always existed in the universe, but gravitational forces of dark matter kept it in check, slowing down the expansion of space during the first 9 billion years of time. This changed 5 billion years ago when the universe grew big enough so that dark matter was dispersed throughout the universe, and dark energy wasn't so affected by dark matter's pull. As a result, the universe began to expand at an accelerated rate.
Dark energy is a constant term. That was probably very insignificant when the universe was hot and dense in the beginning, and so it doesn't really matter whether dark energy is there or not. It is there, but it just plays no role at all. And then as the universe gets cooler and less dense and bigger, so gravity becomes less important, and then dark energy takes over. It's a property of space that we don't yet fully understand.
As the universe expanded, astronomers realized dark energy won its struggle with dark matter and started the acceleration 5 billion years ago.
So there came a time, about 5 billion years ago, when the dark energy started dominating over the attractive matter in the universe. So in a sense, if you plot the force versus time, the gravitational attraction is declining with time, the repulsion is increasing with time, and about 5 billion years ago, the two curves crossed, and that's when the universe started accelerating in its expansion.
Dark energy is fundamental to understand because it tells us where the universe is going. What's the fate of the universe? Is it going to expand forever and get cold and dark? Or is there, some end in sight?
Dark energy now drives the expansion of the universe, and it doesn't seem to be stopping.
The repulsive effect of the dark energy increased because the more space there is between galaxies, the greater is the cumulative effect of the dark energy, the repulsive effect.
And individual galaxies seem destined to a lonely existence.
So it looks as if this is the end of everything.
Surprisingly, the theory of dark energy was proposed and discarded long ago from one of physics' greatest minds. He called it his biggest blunder. His name was Einstein, and he might have been onto the greatest discovery of the 21st century 80 years before anyone had a clue. Science now understands that dark energy is creating and expanding space. But in the early 20th century, astronomers believed the universe was only as big as the Milky Way and would never grow in size. But Einstein had just formed his theory of relativity and decided to test it on the static universe. But as hard as Einstein tried, he could not balance his equation to equal a static universe. His calculations showed a universe that must either expand or contract.
He realized that if you had a universe that was smooth, that was uniformly distributed with stuff, his theory unambiguously predicted that it should either be expanding or contracting.
So Einstein proposed a repulsive vacuum energy that would hold the universe in balance with attractive gravity. He called it his cosmological constant, a constant energy that would hold the universe in balance.
He introduced the cosmological constant, or dark energy, to hold the universe static.
When Hubble announced space was expanding, suddenly Einstein's cosmological constant seemed irrelevant, and he labeled it his biggest blunder.
Now it turns out that dark energy, the concept that he threw away back in the 1920s, is in fact the dominant force blowing the universe apart. Einstein's so-called blunder will eventually determine whether or not the universe dies in fire or ice. And the betting is the universe will die in ice.
In trying to survey how the universe behaves, Einstein had erroneously predicted dark energy and what is the total makeup of the universe.
The total amount of stuff in ordinary matter and dark matter is not enough to account for the curvature of space that we observe.
Like looking across a horizon on Earth, the size of the universe is so great the curvature of space appears flat.
Add ordinary matter, and dark energy together. That makes a prediction for the curvature of space, and that prediction comes spot on. You get the right answer.
Our satellite data now has revealed the fact that 73% of the matter-energy content of the universe is dark energy. Dark energy, which was once Einstein's blunder, is now known to be the dominant force in the universe.
His blunders are our great discoveries.
Scientists are at the very beginning of understanding what effect dark energy will have on the fate of the universe.
Ideally, we'd like to measure how dark energy is behaving as the universe ages.
Eventually, when the dark energy completely dominates over dark matter, the universe will enter a stage known as exponential expansion. For every given unit of time, it'll double in size. And unless the dark energy changes sign someday and becomes gravitationally attractive, the fate of the universe is to expand forever, more and more quickly with time.
We don't understand, if the vacuum energy is driving the acceleration of the universe, why it has the amount it does. That is one of the deepest puzzles remaining in theoretical physics today.
Trillions of years from now, it's going to be a very lonely place. We'll look up in the sky, and the skies will be practically dark. The oceans will freeze over, and it looks as if this is the death of all intelligent life. It looks as if dark energy and the laws of physics are a death warrant to all intelligent life in the universe.
In discovering dark matter and dark energy, science is one step closer to defining the theory of everything. One equation that will define the entire workings of the universe.
Once we have the theory of everything, we'll be able to answer some of the deepest questions ever since man and women first looked at the heavens. This could be the crowning achievement of 2,000 years of investigation into the laws of nature ever since the Greeks asked the question, what are things made of?
For now, dark matter and dark energy continue to be the greatest cosmological questions of the 21st century.
It's certainly frustrating, yes. I mean, it's humbling, too, to know that, all we know about physics is restricted to normal matter, and yet there's all this other dark matter and dark energy that we really understand very little about.
It's the beginning of a new era and the mysteries of the dark side of the universe.
It's the Wild West as far as particle astrophysics, which is what we call this field.
It's a property of space that we don't yet fully understand.